Hello everyone, and thanks for watching Edupedia World videos. In this session of atomic structure, we'll study Heisenberg's uncertainty principle. Okay, so now, like I told in the last session, we have entered a new subsection, an entirely new subsection called quantum mechanics. Okay, with the start of wave-particle duality as given by de Broglie. Okay, as discovered by de Broglie, and now Heisenberg's uncertainty principle is further going to add into our knowledge of wave quantum mechanics. Okay, so what is the uncertainty principle? As per Heisenberg, he said that it is impossible for us to simultaneously determine position and momentum of a particle. Okay, so position is location. For example, where are you situated right now? So now, since you might have studied coordinate geometry in 2 dimension, I'll give you x and y coordinates that this is the exact location of me. In 3 dimension, I'll give you x, y and z coordinates that this is my exact location. This is how you can find out the position. So if I'm trying to find out position of, say, an electron inside the atom, so that position is, let's say, x. So now if I at the same point, at the same time, I also want to determine the momentum of the electron. Momentum is what? Mass into velocity. So Heisenberg states that it is physically impossible to do that. I cannot simultaneously measure both momentum and position accurately. Alright, so it is impossible for us to determine both momentum and position of an object simultaneously. Okay, you can determine one thing at a time, but you cannot determine both the quantities at the same time. Okay, so let's say momentum p is equal to m into v, that is mass into velocity, and position is x. So you might have studied errors and in units and measurements, right? So if p is my momentum, okay, let's say if I'm able to measure momentum p, then you know that there is always going to be some error related to that measurement of momentum, which we can refer to as delta p. Okay, so delta p implies error in measurement of momentum. Okay, error in measurement of momentum. Alright, and let's say the position or the location of the particle of the object is denoted by x, then error in measurement of x will be delta x. Okay, so delta x and delta p, these are errors in our measurements. Okay, which is quite common phenomena. Okay, in measurements you always have some error associated with whatever you measure. For example, if your height is, let's say you say to someone that your height is 160 centimeter. Okay, so now this height 160 centimeter, okay, this is not complete data. A scientist will first denote this into scientific notation, and he will also write something, say plus minus 0.0003 centimeter. So this denotes 0.003003 centimeter, the error in your measurement. That is, your height can be 160.0003, or it can also be 160 minus 0.0003, which will come out to be 159 point something. Alright, so this is what error in measurement implies. So in this case, this 0.0003 centimeter will be your delta h, that is error in your height h. So similarly, we will have some error in the position, which is delta x, and some error in the momentum, which is delta p. Okay, now see momentum further. We know that momentum p is equal to mass into velocity, right? So delta p, okay, delta p can be written as m into delta v plus v into delta m. But now we are going to assume here that mass of any object is being accurately determined by us, right? Since Heisenberg's principle, uncertainty principle, doesn't state anything about mass, we'll assume that mass is known to us accurately. That means delta m becomes 0. That is, there is no uncertainty in the measurement of mass. So this implies delta P is equal to m into delta V. Alright, so error in measurement of momentum can also be calculated as mass multiplied with delta V, where delta V is error in measurement of velocity. Okay, error in measurement of velocity. So now we know what is delta P and now we know what is delta X. So let's study the equation of Heisenberg's principle. So Heisenberg said that I cannot simultaneously determine both the quantities, right? Which means there is always going to be at least some minimum value, okay, some minimum value of the error which I obtain. Alright, that is, I will always have, say, some error in position and I will always have some error in momentum. So what is the minimum error which I can obtain? Okay, so if as a scientist or as a student or as a academician, we always want to be accurate with our results. So what is the most accurate result that I can obtain? The most accurate result will have least error. And what is the least error? So that least error was calculated and was found to be equal to h, okay, divided by 4 pi, where h is the Planck's constant, 4 is 4 and pi is 22 by 7 or 3.14, so on. Alright, so Heisenberg's uncertainty principle states that the product of error in position and error in momentum is always going to be greater or equal to h by 4 pi. Alright, that is, the minimum value of the products of the two errors is going to be h by 4 pi. And as a normal person, okay, as an average human being, you can expect that your error is going to be greater than h by 4 pi. Okay, so if you're Einstein or someone like, if you're Heisenberg himself, so maybe you can calculate to most accurate results. You can make your measurements up to most accurate results. So even those most accurate results will have a minimum error of h by 4 pi in the product of position and momentums. Okay, so this h by 4 pi can also be written as, okay, and it is often written as h cross divided by 2. If you remember, we have studied that h cross is h by 2 pi. Okay, h cross, since h by 2 pi is quite a common number in quantum mechanics, okay, this term is quite common, so we have given it a new variable h cross. Okay, we have studied that before in a previous session. So this is what Heisenberg's uncertainty principles equation is. Okay, and you have to memorize this equation. Okay. So let's go into further detail of this equation. Now we just saw that momentum delta P can be written as m into delta V. Alright, so instead of measuring error in momentum directly, I can instead measure error in velocity, okay, and use that over here. So just substituting delta P as m delta V, I get delta X multiplied with m delta V greater or equal to h cross by 2. Right, so from here, this m, mass is constant, delta X is error, delta V is error, and m is mass. Okay, so I can simply take m mass on the right hand side. Okay, for a given object, mass m will be constant, so this gives me another equation for Heisenberg's uncertainty principle, which is that the product of error in position and error in velocity is always greater or equal to h cross divided by 2m, where m is the mass of the object under observation. Okay, that is the object for whom we are carrying out the measurements. Alright, so for an electron, m will be equal to 9.1 into 10 to the power minus 31 kilogram, and h cross is h by 2 pi, where h is the Planck's constant. Alright, the same Planck's constant which we have studied, 6.636 into 10 to the power minus 34 joules second. Right, so you can remember any one equation, okay, preferably this momentum into look position 1. Alright, and from there you can derive the position into velocity equation. Okay. So from here you can further judge why it is impossible for me, why it is impossible for me to simultaneously measure accurately both position and momentum. Let's assume that, for instance, you are able to measure one quantity accurately. Say I can measure momentum accurately. This will imply that error in measurement of momentum is 0. Okay, and if that is the case, then my delta x will become greater or equal to h cross by 2 delta p. But assuming that error in measurement of momentum is 0, okay, delta p tends to 0. So this would mean that error in measurement of my position becomes infinite. That is, as I keep on decreasing the error in momentum, my error in position will keep on increasing. Okay. So this means more accurately the momentum I can determine, less accurately will be my knowledge about position, and vice versa. More accurately the position I determine, less accurate will be my knowledge about momentum of the object, and momentum of the object can be replaced with m into v, right? So more accurate my result of position is, less accurate will be my result of momentum, or less accurate will be my result of velocity. Alright, so just remember this analysis. So why is this so? Okay, why can't we simultaneously determine both position and momentum? See, basically this concept is inherent to quantum mechanics. Alright, so basically it is, you can assume that it is an implicit property of quantum states itself. So irrespective of our observation or the technology that we use, it is not a case of having bad measurements. Okay, it is not a case of having bad technology. It is not a case of making human errors in your measurement. These errors are implicit to any quantum state. So even if, let's say, it's an inanimate object, okay, say a computer is making the measurement, so even that computer will have to follow this uncertainty principle. Okay, so even if that quantum states, those subatomic particles are not being measured, so even if those subatomic particles like electrons are not being measured, they will be following uncertainty principle. Heisenberg tried to explain this in a certain way, okay, though it is not accurate depiction of its principle, his principle, but we'll try and understand, okay, in a simpler way why this is so. Let's say you have an electron over here, okay. Now this electron is just lying over there, say on the table. Now to observe, okay, to observe the electron, okay, I want to measure its location, its position. So if I want to estimate its position, I need to be able to observe the electron. So I need to be able to see the electron present with me. Okay, so this is our eye. Alright, so to see the electron, I will have to use visible light. Okay, visible light is the only electromagnetic radiation which we can see. So that means I will have to bombard the electron with visible light. Now that visible light, okay, will strike the electron, okay, rebounds, alright, and now this after after reflection, this visible light can be observed by me to determine the location of the electron. But ultimately visible light is also a photon. Okay, it is an electromagnetic radiation, which means it is a photon having energy h into nu. So this energy carrying photon strikes the electron, say at rest, okay, or let's say it is moving with a velocity v, doesn't matter, okay, it is moving with a velocity v. So this is something like, okay, collision between two particles, which you might have studied in physics. Alright, so velocity and mass of first particle and velocity and mass of second particle. So whenever two different particles, okay, are colliding with different momentums, then after collision there will be changes in the momentum of both the particles, right? It is quite possible that the momentums of both the particles get changed as a result of collision. So similarly, this photon with energy h nu is striking the electron with energy half mv square, where m is mass and v is velocity of the electron. So that means there might be some energy transfer between the two. Okay, so that means the energy of your electron after the collision of photon or after the collision of the light ray might change. So the velocity of the electron might change. This means that though you have been able to determine the location of your electron, okay, by bombarding it with light rays, this bombardment has resulted in change in energy or change in velocity of your electron. That means the momentum which you knew earlier, okay, of the electron is now no more its momentum. Its momentum has changed. So again, this means there is going to be some uncertainty in the measurement of your momentum now, right? So that is why you can say that it is not possible for me to simultaneously accurately determine both position and momentum. Okay, now this is just a crude depiction of how uncertainty principle works. Okay, this is not accurate, it is actually an implicit property. Alright, so even if our observation skills are very good, let's say we don't even have to use light ray to observe, even then uncertainty principle will be valid, right? So do remember that. Alright, and another thing, in fact we'll just look at the analysis and there we'll see how this uncertainty principle operates even to macroscopic objects, right? So first thing that we need to understand here in the conclusion part is the unknown trajectory. Right? See, as a result of Heisenberg's uncertainty principle, I can now say that I cannot accurately determine trajectory of an object. What is trajectory? Trajectory is the path which a certain object is going to take. In order to determine trajectory of an object, I need to know its current location and I need to know the direction and speed at which it is moving. Okay, that is its future velocity, its velocity. So I can determine from that location where is it going to be in the future. Alright, so for example, you are over here standing, alright, and you start running. Okay, you start running, okay, 100-meter dash. Right, so now I know your current location. Now in order to determine where you will be after 5 seconds, okay, I need to know in which direction you are running and at what speed you are running. That is, I need to know your velocity. Okay, but since I cannot simultaneously know both your velocity and your location, it is not possible for me to determine your trajectory, or it is not possible for me to predict precisely where you will be after a certain amount of time or at any time. So this, when applied to electrons, can be said that the trajectory of electron cannot actually be known to us. So this is where Bohr's model fails. According to Bohr's model, the electron's trajectory is fixed. Electron revolves in fixed circular orbits. But since I cannot precisely know the trajectory of electron, I cannot state this in, in unambiguous way that the electron is going to revolve in this certain circle of this certain radius. Okay, I can just assume that my electron might be over there. I can just estimate that it might be there, but it might not also be there. Right? That means the trajectories of electron is not known to us. So the circular orbit, okay, the circular orbits as proposed by Bohr are actually not possible. Okay, or at least we cannot say that they are possible with certainty. Next, we have to change all our statements from precision to probability from now onwards. Okay, in fact, now in quantum mechanics, you will see that we can no more talk about precision or that anything is accurately or precisely known to us. We'll always refer to everything as probability. So if somebody asks you what is the energy of your electron, it is probably equal to this. So where is the electron right now? It is probably located at that location. So we'll always, okay, understand the meaning of probability as implicit in all our statements. Last, this Heisenberg's uncertainty principle is significant only for microscopic objects. See, you can apply the principle to both microscopic as well as macroscopic object, but numerically it comes out that it is significant only for microscopic object. What makes the principle significant and not significant? The principle talks about errors in measurement. Okay, delta x, delta v greater or equal to h cross by 2m, right? So if the errors are very large, the value of delta x and delta v is large, then my results are significant, my principle is significant. Alright, that is, I can say that there is so large an error in my value, okay, in my measurement, that Heisenberg's principle can be seen to be applied over here. Okay, this means I am actually unable to measure the location and velocity. Okay, but if the errors are very small, very small, then I can say that I don't have to take into account the Heisenberg's principle. Okay, the error is so small that I can simply neglect the error and I can say accurately that my velocity is so and so and my position is so and so. Okay, so this error part becomes very low. The value of product of delta x and delta v becomes very low for macroscopic or for big objects. Why? Because the value of m for them is very high. So even if you take, say, a tennis ball, alright, or even if you say a table tennis ball which might weigh a few grams, okay, so even that small mass is large enough, okay, to make this whole quantity h cross by 2m very small, so small that the product of errors is insignificant for us. Okay, and it is so insignificant that we can neglect the errors in case of macroscopic objects, but in case of subatomic particles like electron, neutron, proton, alright, atoms, even atoms as a whole, the mass is so, okay, the mass is so low, alright, m is so low that this whole ratio is big enough for us to be able to measure the product of, okay, errors to a significant value. Alright, that is, the errors are significant enough for us to take into account. Right? That is why for microscopic objects the Heisenberg principle becomes very important. Alright, so do remember that. In the next session we'll try to do some numericals on de Broglie's hypothesis as well as Heisenberg's uncertainty principle. Okay, and as soon as we are done with those numericals, we'll study the quantum mechanical model of atom. Okay, this is going to be the last atomic model that we study in this chapter. Okay, and this atomic model is now what you can assume to be most accepted around the world. Okay, though even that is not going to be accurate at our level, but we'll study some basic parts of it. Right, so until next time, and once again, thanks for watching Edupedia World videos.